In the last video, we talked about how after a series of early stumbling evolutions, vertebrates finally stepped onto the stage of evolutionary history. Although vertebrates had achieved the great feat of reshaping the nervous system before this, a question always comes to mind. For a filter-feeding animal, was this series of evolutions really worth it? After all, until over 500 million years ago in the Middle and later Cambrian period, swimming and filter feeding was a very contradictory way of life. Because compared to filter feeding fixed at the seabed, swimming filter feeding consumes more oxygen and energy, and it's not necessarily able to obtain more food. Muscles developed for movement always make predators more covetous. But with the clumsy swimming ability of early vertebrates, how much chance of winning could they have in this cat and mouse game? Things seemed to be going in the wrong direction. However, at this time, in the late Cambrian period 490 million years ago, plankton experienced a great explosion. This is good news for any filter-feeding animal, and swimming filter-feeding vertebrates are no exception. From the start of the Ordovician period 480 million years ago, a group of vertebrates quickly became one of the most common animal groups in the ocean. They greatly enhanced their mobility and evolved mouth structures like monsters in horror movies, becoming the mainstream small predators in the ocean at that time. Then, this group of vertebrates, after hundreds of millions of years of evolutionary efforts, all went extinct. This once flourishing group of vertebrates is known as conodonts. Although, based on numbers alone, their fossils are countless, but since basically only their teeth can form fossils, paleontologists only realized in recent years that they were a group of vertebrates. So, who exactly is the ancestor of modern vertebrates? To answer this question, we have to go back to the Ordovician period again. When it comes to the vertebrates of that time, they could only be described as marginal species. Take the Ostracoderms, for example. It looks just like a hammer. It has a thick layer of armor on its body, yet it leaves a fishtail exposed, stubbornly and playfully showing the world that it can still swim. So how did the Ostracoderms survive in the Ordovician period? It's simple. They could wriggle their tails to quickly bury themselves halfway in the sand and mud. As a result, creatures with poor eyesight like the Megalograptus might swim directly over them, completely unaware that their prey is right beneath them. Other vertebrates from around the same time as Ostracoderms, such as Sacabambaspis and Arandaspis, etc., had basically the same body pattern, a large helmet and a fishtail. They looked like a bunch of swimming hammers. They were called Ostracoderms. This inexplicable outfit caused the Ostracoderms a lot of trouble. Throughout the entire Ordovician period, Ostracoderms were very inconspicuous characters. From the perspective of that time, I would even think that they seemed like an attempt by vertebrates on the armored path. At the end of the Ordovician, animals experienced the first extinction event since their birth, the end Ordovician mass extinction. I've mentioned this extinction event many times in my previous videos. If you're not familiar with it, you can check out these videos. However, it was this mass extinction that brought a glimmer of hope to the Ostracoderms, although this hope came at a great cost. After the mass extinction, Ostracoderms generally continued their swimming filter-feeding lifestyle. However, the intrusion of some uninvited guests brutally broke this tranquility. That would be the sea scorpions. Around 440 million years ago in the Silurian period, various types of sea scorpions entered their golden age. The various large sea scorpions, represented by Pterygotus, firmly occupied the top position of the food chain. Like the previous Megalograptus, they naturally would not let go of the plump Ostracoderms. These Ostracoderms were just a group of gentle filter feeders, but in the survival of the fittest in the Silurian Ocean, they could only survive in the gaps among various predators. Under this enormous survival pressure, the Ostracoderms began to explore new body structures, thus ushering in the most varied era of ostracoderm morphology. For example, there was a type of ostracoderm called pterospidomorphy. They began to break down the original monolithic head armor into several plates, while strengthening the scales on the back half of their bodies, looking exactly like an ancient warrior in plate and scale armor. which to some extent balanced defense and movement. On the contrary, there was another type of Ostracoderm that did not live up to its name, Anaspida. They abandoned their body armor early and went into battle lightly equipped. Our modern-day lampreys are likely descendants of this group of vertebrates. However, the final victory in these many evolutionary attempts was achieved by a type of Ostracoderm called Osteostracia. They made several major breakthroughs that allowed vertebrates to develop and grow from then on. Externally, they evolved a bony armor. The armor composition of the previous Astraspis and Heterostraci was closer to our teeth. Although the material was hard, its dense structure also made the armor too heavy. However, the bony armor of the Osteostracia is somewhat similar to our bones, with a porous interior to balance toughness and lightness. Internally, they developed a cartilaginous endoskeleton. These cartilages wrap the original notochord and dorsal nerve tube, creating the prototype of today's spine. The most important point is that the Osteostracia profoundly transformed their nervous system. They wrap their nerve fibers with a layer of fat-rich insulation called the myelin sheath. This composite nerve structure greatly optimized the efficiency of nerve signal conduction, increasing the conduction rate by a full 100 times while making the nerves more energy efficient. If the previous reconstruction of the central nervous system was the optimization of the overall architecture, then the myelin sheath is undoubtedly a revolution in basic hardware. From this point on, vertebrates were no longer on the same level as the rest of the animal kingdom in terms of their nervous system. Under the combined action of this unparalleled nervous system and the cartilaginous endoskeleton, the Osteostracia evolved an organ with a far-reaching impact for vertebrates: the paired fins. The dorsal and tail fins of most fish, which are located on the body's central axis, are called single fins. They can provide strong propulsion, but easily cause the body to lose balance. The paired fins on the sides of the body perfectly compensate for this shortcoming, granting the Osteostracia powerful maneuverability and making them the most agile creatures in the ocean. However, at this point, there was still a slight gap between vertebrates and becoming the dominant species. As I've said before, the Silurian period was mainly the era of the sea scorpions. Under the oppression of these predators, although the Osteostracia already had some advantages, they found it hard to turn these advantages into a final victory. The feeling of unparalleled agility and mobility could only be used for barely surviving under the rule of the sea scorpions. However, true peace is not something to be pleaded for. Over 420 million years ago, it was a time that seemed just like any other. However, in the place equivalent to modern-day Qijing, Yunnan, China, which was a rich and isolated shallow sea at the time, an event occurred that would be recorded in the history of vertebrate evolution. Yes, the sea scorpions were defeated. This sea area was like the weakest link in the empire of the sea scorpions. Not only were the sea scorpions there in small numbers, but they were also relatively small in size. However, it was here that the first domino of the sea scorpion's empire fell. Here, the vertebrate's evolutionary potential, accumulated over 100 million years, finally exploded. All of this started when a certain class of Osteostracia transformed two pairs of gill arches into jaws. From then on, a new force known as Gnathostomos entered the stage of history. Indeed, Yunnan, China, is truly a fortunate place for vertebrates. The first two major revolutions in the history of vertebrate evolution took place here. The emergence of jaws finally gave vertebrates a weapon to compete with other predators. More importantly, it freed the function of the pharynx for feeding. From then on, the pharynx essentially contracted into a tube. A large amount of space in the head was freed up, clearing the last obstacle for the evolution of the vertebrate brain. The earliest known fish with a complete jaw is called the Entelognathus, which is about 30 centimeters long. It might have seemed somewhat clumsy by today's standards, but the Entelognathus had already started preying on small animals, making its way up the food chain. Yes, the historical process of vertebrates dominating the world had begun. Not long after, species like the Megamastax amblyotus appeared, which were regional predators at the top of the food chain and measured over a meter in length. By the end of the Silurian period 20 million years ago, the ancestors of all the various branches of vertebrates we know today had already made their appearances. Soon these rising stars of the animal kingdom were no longer satisfied with this rich shallow sea. From here, they set off towards a wider world. Why did vertebrates come to dominate the world? Some say it was because of the jaw. Others say it was because of their mobility. But the truth is more complex than these blunt answers. The success of vertebrates lies in their size, a pure physical overpowering. The size increase in animals is restricted by many factors. For free-moving animals, the speed of nerve conduction is a hurdle that cannot be crossed. Invertebrates generally have nerve conduction speeds of only about 1 or 2 meters per second, perhaps even slower than you walking. As a result, once their size reaches 1 or 2 meters or even more, they inevitably become clumsy and slow. The Gecalopterus rheninae of the Devonian period could reach 3 meters in length, but they could only be scavengers because they could no longer drive their bodies to perform too refined movements. The cephalopods of the Ordovician period could reach 10 meters in length, but the vast majority of that was their shell, with their soft parts limited to a range of about 1 meter at the front end of their body. Later cephalopods increased their nerve conduction speed to 25 meters per second by thickening their nerve fibers. But how many of such thick nerve fibers could fit in the body? Only vertebrates have super nerve fibers with a transmission rate of over 100 meters per second. Coupled with a very reasonably arranged nerve center, they don't have to worry about not having enough nerves no matter how large they get. Therefore, from the Devonian period 10 million years ago, there emerged a group of jawed fish with generally larger sizes. They were known as Placoderms. For example, the Dunkleishus that appeared in the late Devonian period between 360 and 380 million years ago is possibly the largest in the Placoderm family. According to different reconstructions, their length is estimated to be between 5 and 9 meters. Their scythe-like mouths could deliver a bite force of several hundred kilograms. They also wore heavy armor. Even their eyes were equipped with a ring of armor, almost completely immune to the pincers and stingers of sea scorpions. They basically evolved specifically to hunt sea scorpions. In other ecological niches, the approximately 8-meter-long Titanichthys, a near-invincible filter feeder in the ocean, demonstrated the feasibility of filter feeding while swimming. Not to mention the herbivores. These giant placoderms, like the Grim Reaper, left a trail of destruction wherever they went. They completely overturned the order of the entire animal kingdom, changing the face of Earth's life in just 10 million years. From then on, the Devonian period had another name, the Age of Fishes. It was from here that vertebrates took the throne as Earth's dominant species, a position they have held for the subsequent 400 million years. However, somewhat ironically, although placoderms took the throne as Earth's dominant species for vertebrates, they did not remain in power. They were the first jawed fish to exit the evolutionary stage during the catastrophe at the end of the Devonian period more than 370 million years ago. But they had fulfilled their historical mission. Shortly after the mass extinction, another group of fish rapidly rose and inherited the throne of placoderms. At the same time, a group of fish not only survived the mass extinction, but also ventured into territories that vertebrates had never before explored. From then on, nothing could stop the conquering journey of the vertebrates.